Hi everyone, welcome back to my YouTube channel. I visited the 2025 Sushi Tech event at Tokyo Big Sight. In the event, I stumbled upon a technology called digital twins. After that, I began to learn the concept, architecture, and implementation example from research papers. So this is my learning summary of digital twin. The summary is divided into 3 chapters. The first chapter is to understand the definitions and the concept of digital twins. The second one is to understand the data movement and processing in digital twins. And the last chapter is to observe an implementation example of digital twins in a factory and try to understand the technology stack. Chapter 1, Definitions and Concepts, the essence of digital twins. Let's try to understand the concepts by looking at a digital twins, or DT for short. Example, in health. Imagine you wear a mobile health device. It continuously captures your health conditions through sophisticated sensors and algorithms. Besides that, you also have a diagnosis and treatment history from the hospital, your environmental and social conditions, and your multiomics such as genetic. This is your physical health entity. Now imagine a system that continuously captures that information to build a unique personalized health model of you. With advanced physics and mathematical algorithms like AI, the model adapts as you grow older. With all this data, the health model can be used to improve your health by predicting your health trajectory and giving tailored health solutions. Karen Wilcox on TED said dynamic twins are a personalized, dynamically evolving model of a physical system. I can summarize that a digital twin is generally defined as a virtual representations of physical systems, object, or process. This virtual representation is dynamically updated with data from its physical counterpart throughout its lifecycle. Let's take a look at the DT cycle. It begins by collecting data from the physical world. It can be done, for example, by using robotics, LiDAR, or light detection and ranging sensors, and IoT. The collected data forms the basis for creating twin of today, representing the current state of the physical entity. The next step is to understand the physical world. This phase involves interpreting and visualizing the data to create a comprehensive understanding of the physical entity. It uses powerful mathematical and statistical models that are learned from the data. When we have the data and the model and it's continuously updated in near real time, we can do data simulations to give predictions or recommendations tailored to this specific object to shape the next versions of the physical object. And before the recommendations are implemented in the physical world, we can test scenarios and outcomes in a virtual environment for the risk assessment. Digital twins benefit. 1. Improve product development and testing. Digital twins provide a risk-free product development environment, allowing more design options to be explored without the cost of physical prototypes. They improve testing and validations by allowing new solutions to be evaluated in a wide range of real-world scenarios. Next, enhance monitoring and information. They provide more detailed information about product behavior, making it easier to monitor the state of any part of the system and track complex interactions. They monitor, manage, and improve the functioning of physical systems by replicating their lifetime. They enable companies to quickly detect and solve physical problems. Next, predictive analytics and maintenance. Digital twins continuously anticipate future states like flows, damages, and failures, enabling the creation and testing of fresh configurations for preventive maintenance procedures. They play a crucial role in predictive maintenance. Next, decision making and optimizations. They provide insights for more strategic decision making and performance optimizations. Modeling and simulation play a vital role in supporting decision making by accurately predicting system behavior. Next, collaboration and transparency. Dependencies between upstream ideas and business performance become transparent, which helps teams collaborate and understand the impact of design changes. Data traceability is ensured by capturing and logging real-time data, enabling transparency and auditability. Let's see a DT study case from Boeing. Improve product development and testing. Boeing used digital twins to create virtual models of aircraft components, allowing engineers to test designs in various conditions before physical conditions. Let's see DT study case from Northumbrian Water Company. Enhance monitoring and informations. Northumbrian Water employs digital twins to monitor water utilities across the UK, reducing the need for frequent site visits and improving assets management. This is a diagram of the 2024 sector-wise distribution of digital twin-based data analysis from recent academic papers. It is dominated by manufacturing sectors, likely due to its maturity in Industry 4.0 practices. Let's go to Chapter 2. Data, the heart of digital twins. Data is often described as the brain or building blocks of any digital twin system, and is considered the core divider between a successful and unsuccessful system. This slide is about a common reference of components for DT applications across different fields. First is a physical entities. These dimensions encompasses the physical assets and industrial system in the real world. Data is collected from these entities to capture their real-time state and behavior. Next, visual model. These dimensions hold diverse digital formats and models such as AI models and 3D simulation models, which describe the physical objects or systems. These models are used to predict behavior, optimize operations, and provide more insight. The next dimension is service. This refers to the services provided by the digital twins. The goal of DT is to provide value-adding service to users such as monitoring, simulations, verifications, virtual experiment, optimization, and digital education. DT can also integrate third-party services like resources services, algorithm services, and knowledge services. DT data. This dimension represents a collection of data which generated from the other three dimensions. And the last dimension is the connections. This dimension represents the connections between the physical entities, virtual model, services, and digital twin data. This connection enables the four other parts to collaborate. So these DT dimensions are considered to have good practicability and scalability. The operation of DT models and services are primarily driven by data. For data-driven DTs to perceive, respond, and adapt to changing environments and conditions, data goes through a lifecycle that includes several steps, involves like data collections, transmission, storage, processing, fusion, and visualizations. This lifecycle is often restructured based on the specific characteristic of digital twins. So the first cycle is data collections. Data can be collected from tangible items, sensors, IoT devices, third-party APIs, and other sources. The collection can be done in real time, offline measurement, or by using sampling inspections. The collected data can be multi-dimensions, multi-source, heterogeneous, or multi-temporal scale. Multi-temporal scale means data collected over multiple points in time, often different temporal resolutions like seconds, minutes, hour, day, or years. Feature data acquisition technologies. It should focus on real-time status data collections. This ensures the virtual model is always in sync with the physical asset. Exploring smart identifications. This reduces manual data entry and errors. And focus development of advanced sensor technologies and machine visions. The next cycle is data transmissions. This is to facilitate real-time data transfer while ensuring that information is not missing or damaged, and that its authenticity is maintained to the greatest extent. Data is typically transmitted using industrial communication standards like Modbus, OPC UA, MQTT, or AMQP. For wire data transmissions, this technology can be used such as Gigabit Ethernet or EPON, Ethernet Passive Optical Network, or GPON, Gigabit Passive Optical Network. Networking technologies that usually used in DTs are NB-IoT, or Narrow Band Internet of Things, LoRaWAN, Long Range Wide Area Network, and Sigfox. This tree is a low power wide area network or LPWAN. And then we have Zigbee and Z-Wave is a short range wireless communication protocol, usually for smart home systems. Future directions involve exploring high-speed, low-latency, high-performance, and high-secure data transmission protocol like Fibre Channel Protocol or FCP. It's a high-speed network protocol primarily used for storage area networks. And quantum transmission technology refers to the use of quantum mechanics to transmit informations. The next cycle is data storage. A data storage system is used to save collected information so it can be processed, analyzed, and managed later. It plays an important role in classifying, sorting, and keeping data and allow quick access and updates when needed. The main goal is to organize, store, and connect the large amount of data found in digital twin systems. Data can be modeled using appropriate modeling languages such as Unified Modeling Language or UML, System Modeling Language or SysML, and Ontology Language. Traditional database technologies are no longer feasible due to the increasing volume and heterogeneity of multi-source data. This is why big data technologies is preferable, including distributed file storage or DFS, NoSQL database, NewSQL databases, and cloud storage. Future direction involves MPP or massively parallel processing. Is a database architecture that distributes data and query processing across multiple independent nodes, enabling high performance and scalability for large datasets and complex analytical workloads. NewSQL is a modern relational database management system that aims to combine the scalability of NoSQL system with the ACID guarantees of traditional SQL databases. And then we have MRAM, It's a data storage media that we can improve also by adopting inductive thin film and magnetic random access memory. It is crucial for data to have consistent representations. The Digital Twin Definitions Language, DTDL, is proposed as a common language for defining digital twins and their relationships. And new mathematical approaches based on category theory could also provide a foundation for modeling interoperability and integrations. The next cycle is data processing. This step is for cleaning, compressing, smoothing, simplifying, and transforming the data. The goal is to convert raw data into clear, usable information that follow specific formats. Data can be analyzed using statistical techniques and or neural network techniques. Statistical techniques include descriptive statistics, hypothesis testing, correlations and regression analysis, or clustering. Neural network techniques such as forward networks, feedback networks, and self-organizing maps. Future data processing include edge and fog computing, graph processing, domain-specific tooling, and advanced AI or ML models. The next cycle is data fusion. Data fusion is the process of combining data from different sources to create a clearer, more accurate picture. For example, if you fuse a jet engine and a wing, you get a digital twin of an airplane, which has a new function like flying. Data fusion can be done in different levels. Raw data level, combinations of data from machine or sensors. Feature level, combinations of processed data features. And decision level, combinations of multiple models. Different methods are used depending on the type and level of data being fused. Random methods. This one is random methods. It's applicable for raw data level, feature level, and decision level fusions. We have weighted average method, which average data based on importance. Dempster-Shafer theory deals with uncertainty. Kalman filters to track and predict changing value, and Bayesian methods to update prediction based on new data. And we have AI methods, primarily applicable for feature level and decision level fusions, such as neural network, fuzzy set theory, rough set theory, wavelet theory, and SVM theory. The last cycle is data visualizations. The goal of data visualization is to turn complex data into easy to understand visuals. With visual, people can be able to spot patterns, trends, or problems quickly, make faster and better decisions, understand how systems and products work in the virtual environment, monitor and improve real systems in real time, see digital data overlaid on physical machines or workspaces using AR. Technologies that can be used. One is charts and graph, like bar charts, pie charts, and other graphs, and also dashboard. Next is Unity or Unreal Engine, used for 3D visualizations. WebGL, to enable 3D visuals in a browsers. CAD software, used for detailed 3D models or equipment and buildings. Apache eChart is an open source tool for interactive visuals from large or changing datasets. Immersive technology, such as AR, adds digital info to the physical world, useful for guiding users in real time, or VR and MR, allow users to explore virtual models. We also have NERV, or Neural Radiance Fields, are a deep learning based method for representing 3D scenes, allowing creation of 3D scenes from 2D images. Point cloud It's a set of data points in 3D coordinate systems. BIM, Building Informations, is an intelligent 3D model-based tool that provides users with digital representations of a physical facility and functional characteristic. So now let's go to the third chapter. In this chapter, we are going to see the design and implementations of the T4 factory. The information is based on the article published by Chang Cho and Sang-do No from Korea. We are going to build a DT factory where users connected to the digital factory can interact with the digital environment, accessing real-time information about the factory status. To build that, we need 3 phases. First is shop floor phase. The first stage, the shop floor phase, involves mechanical equipment such as machines, robots, and sensors that can collect and transmit data via edge computing. And then we have digital twin factory phase. Collected data are sent to the digital twin factory, where real-world factory conditions are replicated in the digital environment, allowing for real-time monitoring. Within the digital factory, the status of machines and facilities can be visualized, observed using 3D modeling, and all data generated in real-world factory is implemented in the digital factory. And user phase. In the final phase, user can access the digital factory to view and control various types of informations. User monitor the digital factory status in real time through multiple monitors and analyze the factory conditions using various charts and data visualization tools. And users can also collaborate with other connected users with real-time voices and videos for effective collaborations. This is the system configurations of DT factory. First, we have physical space. The physical space layer includes real-world machinery, equipment, and personnel. This layer collects operational data from physical factory machines and equipment, transmitting them to the digital twin. Data are collected through PLCs and sent to the edge computer. Additionally, factory personnel can provide operational information via voice and video data using HMD or head-mounted displays, desktop computers, tablet computers, or other supported device. And then we have communications layer. The communications layers links the physical and digital spaces for data transmissions. This layer manages the real-time transmissions and processing of data from the physical factory to a centralized database via OPC UA and MQTT protocols. The WebRTC protocol is also utilized for real-time voice and video streaming. And last is the digital space layer. The digital space layer encompasses a digital environment that includes a machine twin and a human twin. This layer organizes, monitors, and controls the digital environment based on real-world data. The machine twin represents real-world machines and facilities digitally, including a digital monitoring dashboard and 3D models. The dashboard enables real-time monitoring of the machines and equipment status, while the 3D models provide visual representations. The human twin represents real-world personnel digitally, incorporating real-time voice and video data. This allows personnel to collaborate in real time with the digital twin factory. PLC or Programmable Logic Controller is a simple computer for industrial automations. Think like a programmable switch. The PLC design contains some basic hardware. First, CPU or Central Processing Unit or microprocessor. This is the part that runs the PLC, the brain of the microprocessor. And PLC has 3 types of memory. RAM, random access memory. This is a temporary memory in use while the program is running. ROM, read-only memory. The operating system of the PLC is stored. And we have EEPROM, or electronically erasable programmable read-only memory. This is a permanent memory just like ROM, but it can be erased electronically and reused. The PLC program is stored here. And we have I/O sections. We have input device, which receive incoming signals from external sensors and then converts them to low voltage digital hints before sending them to the processors. And then we have output sections, which receive low voltage digital signals from the processing unit and converts them into high power hints. And then we have programming sections. These sections enable inputs into the PLC control via keyboard, for example. It used to program and troubleshoot PLC. So on the left side is the picture of PLC device example, and on the right side is the screenshot of PLC programming software. One of the examples of PLC usage in our daily life is traffic light controller. These traffic lights are monitored and controlled by PLC hardware and software. For example, if a person wants to cross the street, he can push a button and it will switch the lights so he can cross the street. Edge computing. Edge computing is a distributed IT infrastructure that brings processing of raw data close to its sources. What does it mean? We have a lot of machines or sensors in the factory. Each of these machines produce data. We put computers close to the factory or maybe inside the factory. The computers and machines are connected by using local network. And this computer will receive data from the machines and do data processing. Only actionable results are eventually transmitted to the main server, often located far away where power and rent are cheaper. The benefits of using edge computing are real-time data collections. Edge computers are placed on the factory floor. The data latency is small because using a local network. On-site data processing. The edge computers analyze and convert raw data using packet analyzer and parser. For example, converting data from PLC to OPC UA protocol. And this enables immediate insight into production status without relying on cloud processing. And last, reductions of network bandwidth and enhanced processing speed. By processing real-time data locally at the factory site before transmitting it, edge computing reduces network bandwidth usage. This also enhances data processing speed, providing an environment where manufacturing data can be monitored in real time for prompt decision making. This is an example of edge computing usage in US Postal. USPS processed 7.3 billion parcels annually and has implemented edge computing with AI at 195 mail processing centers. Edge computing avoids building a full data center at each site. Tracking a missing package now takes less than 2 hours instead of days. MQTT. MQTT, or Message Queuing Telemetry Transport, is a lightweight client-server publish-subscribe messaging transport protocol, typically used for communication in M2M or machine-to-machines and IoT applications, where a small code footprint is required and or network bandwidth is at premium. MQTT requires TCP/IP. It uses persistent TCP connections. So TCP guarantees the package will be transferred and reliable. MQTT architecture is based on PubSub model. MQTT client can be a publisher or a subscriber. The data is published and will be received by MQTT broker or a cluster of broker. Another MQTT clients subscribe to the topic, and the broker will push the data to all subscribers. Open Platform Communications Unified Architecture is a specification standard for platform-independent client-server for M2M communications. It has OPC UA information models, which is a structured semantic description of data and behavior. OPC UA can also run over PubSub model using MQTT. The simplified architecture of OPC UA. So we have field connections like PLC, Modbus, or other. They are connected to the OPC UA server to send and receive data. At the other end, there are OPC clients like HMI or Human Machine Interface, Edge Server, and other. These clients can receive and or send data to OPC UA server. WebRTC stands for Web Real-Time Communication. It's a peer-to-peer communications between clients to exchange video or audio. How does it work? In WebRTC, it requires a signaling server to establish the connection for the first time. Client 1 will share his information to signaling server. Signaling server will inform client 2 that client 1 wants to connect along with his information. If client 2 accepts it, client 2 will share his information to signaling server. Signaling server will inform the client 1 about client 2 information. And after both clients agree to connect and know each other information, they can start exchanging video or audio directly. It uses UDP, so sharing files is not recommended because the package can lose. LiDAR stands for Light Detection and Ranging. It is an advanced laser-based device used for capturing high-precision 3D data of surfaces, landscapes, and objects. A LiDAR scanners work by emitting laser pulses toward a target surface. These pulses reflect back to the sensors, and the time taken for their return is used to calculate precise distances. This data is processed to create 3D models, terrain maps, and point cloud datasets. What is point cloud? A point cloud is a collection of data points in a 3D coordinate system used to represent the surface of an object or a space. On the left side, I have point cloud of a bathroom. The collections of data points shape into 3D representations of a bathroom. Point cloud data can consist of spatial coordinates like the X and the Y and the Z, color informations if the scanner can capture color informations in RGB format, and the intensity of the lights or lumen values. LiDAR scanners can be mounted on various platforms including airborne drones, vehicles, and stationary tripods. In this example, a man is carrying the LiDAR scanner device. He walks around the factory to scan the factory, and on the left side is the 3D models of the factory based on the point cloud data. The 3D models created from LiDAR scans were integrated to the Unity environment, followed by additional post-processing to optimize the factory layout as shown in the image. This process allowed users to visually interact with a digital space that closely mirrors the real factory environment. A digital dashboard was developed to monitor real-time data within the digital factory. Data collected by the edge computer was transmitted to the dashboard in real time, enabling instant monitoring of the equipment status. This setup allows users to access real-time information from the physical factory within the digital environment. That is all, my friend. Thank you for watching, and until the next video, keep learning and stay healthy. Bye-bye.